Welcome to AI Paper Podcasts. Today, we're looking at a really interesting one, FlowRL, matching reward distributions for LLM reasoning. Seems like a potentially foundational paper.
Absolutely. It really gets into the weeds of a persistent challenge with reinforcement learning for large language models.
You mean applying RL to things like chain of thought reasoning?
Exactly. Especially the problem of mode collapse that often plagues the standard RL methods like PPO or GRPO when you try to fine-tune these models for complex tasks.
Okay, so FlowRL is proposing a different way forward then.
That's the core idea, yeah. It's a pretty fundamental shift. Instead of just trying to maximize a reward signal, which is what PPO and GRPO do,
Right, find the single best way to get the reward.
FlowRL aims to match the entire distribution of potential rewards. It uses this flow balancing idea.
How does it do that technically? Like in a nutshell for the quick summary.
Okay, so it takes the scalar reward, the score, and turns it into a target probability distribution, tilde tilde boss. It does this using a learnable normalizer, this partition function ZFO.
Got it. So it defines a target distribution based on rewards.
Right. And then the model's policy is trained to match that target distribution by minimizing the reverse KL divergence. The key is it encourages exploring all high-reward paths, not just the most obvious one.
And this actually worked. Did it show improvements?
Oh, yeah, definitely. The results are pretty striking. On math benchmarks, FlowRL averaged about 10% better than GLPO and 5% better than PPO in accuracy.
Wow, 10% over GRPO is significant.
It is. And it wasn't just math. They saw consistent gains on code generation and reasoning tasks, too. Better generalization, more diverse solutions. It seems to hold up.
Okay, so today let's really unpack the technical side, how this distribution matching works, the theory behind it, and importantly, how they actually made it work for these, really long reasoning sequences.
Sounds good. It's a great blend of theory and some clever engineering.
All right, so let's start with the problem FlowRL is designed to fix. You mentioned mode collapse with PPO and GRPO. Why is that such a big deal, especially for reasoning?
Well, it's sort of baked into the objective function of those algorithms. They're designed to maximize the expected reward. And when you optimize for expectation, the policy very quickly learns to identify the dominant mode, basically, the type of solution path that yields the highest reward most often.
And then it just keeps doing that, overfitting to that one strategy.
Precisely. It becomes really good at that one thing, but it stops exploring other potentially valid, maybe even better in some cases, ways to solve the problem.
So you lose diversity. If there are, say, 10 ways to solve a math problem correctly, the model might just learn one and ignore the other 9.
Exactly. And that lack of diversity really hurts when you need to generalize, especially in these long chain of thought processes where maybe the first few steps look familiar, but then you need a different approach later on. The model gets stuck.
Now, GRPO is often used because it avoids needing a value function, right? It just compares groups of outputs. Does that make the mode collapse worse compared to PPO?
That's a good point. PPO still uses a value function to estimate the advantage, which gives it some sense of the broader reward landscape, even if it's noisy.
Okay.
GRPO, by relying only on comparisons, simplifies things maybe too much. It makes the policy updates really sensitive to finding just any high reward peak and then hammering away at it.
Yeah.
So yes, arguably it can accelerate that mode collapse.
The paper had that figure comparing KL divergence, didn't it?
Yeah, that illustrated it really well. Methods like GRPO focused on one peak had a really high KL divergence from the true reward distribution they mentioned, a value like 8.68.
Meaning the model's output distribution was very different from the ideal target distribution.
Right. Whereas FlowRL, because its goal is to match that target distribution, achieved a much, much lower KL divergence, something like 0.11.
Wow, orders of magnitude difference.
Exactly. It's solid evidence that the policy learned by FlowRL actually covers more of the underlying solution space, capturing that diversity.
Okay, so let's dig into the FlowRL mechanism itself.
Yeah.
The core idea is matching this target distribution, tilde define, which they define using that exponential through reward. But how do they actually optimize against that? You can't just list all possible sequences, right?
No, you definitely can't. That's where the learnable partition function, ZFi, comes in. It's the key piece that normalizes the beta RRXY term, making it a proper probability distribution that sums to 1.
So ZFi represents the total reward mass over all possible sequences for a given input X.
Essentially, yes. And learning the CFI and optimizing the policy theta to match the stable distribution by minimizing the KL divergence. Well, that's where things get computationally interesting and where the connection to GFlowNets comes in.
All right, this was a really cool part of the paper. Proposition 1 connects minimizing this KL divergence to minimizing the trajectory balance loss from GFlowNets. What's the intuition there? Why are these two things equivalent?
It's about flow conservation, basically. Think about probability mass flowing through the sequence generation process.
Yeah.
To perfectly match the target reward distribution, which is what minimizing KL divergence does, the amount of probability mass flowing towards any final sequence Y must end up being proportional to its reward on the scalars.
Okay.
GFlowNets achieve this by enforcing a balancing condition at every intermediate step, or state dollars, in the sequence generation. The trajectory balance loss, the TB objective, essentially says that the total flow into any state dollars must equal the total flow out of state solars.
So it's not just looking at the end reward, it's ensuring consistency throughout the whole path generation.
Exactly. It enforces this conservation law step by step. If file dollars is the sort of total expected reward flow through state, the TB loss makes sure that files equals the sum of flows going out to the next state's sophist dollars weighted by the policy probabilities.
And forcing this balance everywhere naturally leads to the final distribution matching the rewards.
Yes, because the only way to satisfy this local balance condition globally is if the flow ending at each terminal state Sata-Levs-Naller is proportional to its reward, Arsa-Naller. It naturally pushes the policy to explore all paths that contribute reward proportionally.
So by using this GFlowNet machinery, FlowRL isn't just matching a distribution, it's doing something deeper.
It is, and that's what Proposition 5 highlights. It shows that FlowRL effectively acts like a form of maximum entropy RL. It's implicitly maximizing both the expected reward and the entropy or diversity of the policy.
So that's the theoretical source of the diversity gain. It's baked into the objective via the GFlowNet connection.
Precisely. It's not just trying to find one good path. It's actively encouraged to find a wide range of good paths.
That theory sounds great, but, applying these things to giant LLMs generating sequences thousands of tokens long,
Yeah.
that's usually where things break down. What engineering hurdles do they face adapting trajectory balance for long chain of thought?
Yeah, the practical side is crucial here. They hit two main roadblocks applying the standard sequence-level trajectory balance objective.
What was the first one?
Exploding gradients due to sequence length.
Because the log probability term, log pay theta, the TB objective, is a sum over all the tokens in the sequence.
Exactly right. If you have a sequence of, say, 8,000 tokens, that sum involves 8,000 terms. In typical GFlowNet uses with much shorter sequences, it's manageable. But with long QT, the magnitude and variance of this term just blew up.
So a sequence that's twice as long could have a gradient signal that's orders of magnitude larger, making training unstable.
Pretty much, yeah. It completely destabilized the learning process. So the fix was relatively simple but essential: length normalization.
What did they do?
As mentioned in Remark 3, they just rescale that log probability term by the sequence length. $1 log pathetic at the store. This puts long and short sequences on a more equal footing gradient-wise and prevents those huge explosions.
Okay, that makes sense. Stabilize the signal. What was the second big hurdle?
Sampling mismatch. The standard KL objective and GFlowNet theory assume you're sampling trajectories from the current policy, on policy.
Right, but for efficiency with LLMs, you almost always reuse data generated by older versions of the policy, right? Off-policy data, like PPO does.
Exactly. Training these models is expensive, so you need that data efficiency. But using off-policy data with an objective derived for on-policy sampling creates a mismatch.
So how did they bridge that gap? Does introducing an off-policy correction cause other problems, like increased variance?
It's always a trade-off. Yes, off-policy corrections like importance sampling do introduce variance, theoretically, but it's often a necessary evil for efficiency.
So they used importance sampling.
Yes, that's the standard fix, detailed in Remark 4. They reweight the contribution of each off-policy trajectory using an importance ratio, dollars, which is basically the probability of the trajectory under the current policy divided by its probability under the old policy it was sampled from.
And they clipped it.
Yeah.
1 epsilon, 1 plus epsilon.
Right, clipping the ratio is crucial to control the variance that importance sampling can introduce, especially if the old and new policies have diverged significantly, and they detached the gradient through the ratio to keep things stable.
And was this correction actually important?
Absolutely critical. The ablation study showed it clearly. Without importance sampling, performance on one task dropped from over 35% accuracy down to about 26%.
Wow, so a huge hit.
Massive. It proves that you really need this correction to make flow balancing work in a practical, data-efficient RL setup for LLMs.
So the final objective, LFlow or RL in equation 6, It's this blend of the core trajectory balance idea adapted with length normalization and importance sampling for real-world LLM training.
That's a perfect summary. It marries the GFlowNet theory with the engineering needed for scale.
Okay, theory and engineering sorted. Let's talk results. Did this distribution matching approach actually pay off on the benchmarks?
It really seems like it did. The quantitative results were consistently strong.
Looking at the math results first, with the Quinn 2.5 3TB model, they hit a 48.4% average accuracy. But you mentioned it did particularly well on the harder stuff.
Yes, that's what stood out. The gains were especially noticeable on datasets like Math 500 and the Olympiad problems. These are tasks where just exploiting one simple trick usually doesn't cut it. You need more flexible reasoning.
Which fits the diversity story. And did that carry over to coding tasks?
It did. Using a DeepSeek-based model, FlowRL came out on top across the board. Highest average score, AVG at 16, on Live Code Bench, hitting 37.4%.
Nice.
And it got a significantly better rating and percentile rank on code forces compared to the baselines. So consistent outperformance in both domains.
Okay, the scores are great. Higher numbers are always good. But the whole point was diversity, right? Did they manage to measure that directly? How do you even measure the diversity of reasoning paths?
That was a really neat part of their evaluation, the diversity analysis. They took solutions generated for AMA math problems. These are quite challenging competition problems. They generated 16 different solutions or rollouts for each problem using FlowRL and the baseline models. Then, crucially, they used GPT-4 Mini as a judge.
Okay, using another AI to judge the diversity.
Yeah. GPT-4 Mini was prompted to analyze the 16 rollouts for a given problem and assign a score from 1, meaning all solutions followed the exact same logic, total mode collapse, up to 5, meaning the solutions explored fundamentally different mathematical strategies.
And what did the judge say?
The difference was really clear. FlowRL scored 2.28 on this diversity scale.
Okay. And the baselines?
The best baseline, which was PPO in this case, only scored 1.31.
So almost double the diversity score for FlowRL.
Pretty much. It's strong evidence supporting the core hypothesis that matching the reward distribution via flow balancing genuinely leads to more diverse exploration of the solution space.
Can we make this more concrete? They had that case study, the AE problem, about the rectangular box. What happened there? How did GRPO fail and FlowRL succeed?
Yeah, that case study really crystallizes the difference. GRPO, the reward maximizer, did exactly what we discussed earlier. It mode collapsed.
How so?
It latched onto a common mathematical tool, the AMGM inequality, arithmetic mean, geometric mean. It just kept applying AMGM repeatedly.
But that wasn't the right tool for the job.
Not entirely. AMGM gives you bounds, but this problem required finding an exact value for the box's dimensions. GRPO got stuck, basically repeating the same ineffective strategy, applying AMGM multiple times, going in circles, and ultimately it couldn't solve it.
It got stuck in its familiar but ultimately unhelpful rut.
Perfectly put. FlowRL, on the other hand, showcased the benefit of diversity, because it wasn't just trying to exploit one known trick, it explored a different path.
What did it do?
It explored a strategy based on symmetry. It tried setting two of the box dimensions equal, AB dollar. This assumption dramatically simplified the problem's constraints.
Ah, a strategic simplification.
Exactly. This led it down a path to a much more manageable cubic equation. 3/27 AT plus 46 equals $.
Okay, and could it solve that?
Yes. This cubic equation turned out to have a rational root, which FlowRL found through factorization, leading directly to the correct answer for the box dimensions.
So, by not being locked into the obvious inequality approach, it found a more elegant algebraic solution path that actually worked.
Precisely. It demonstrates how escaping that pull towards the dominant mode allowed FlowRL to find a fundamentally different, and in this case, successful, reasoning strategy. It wasn't just doing the same thing slightly better, it was doing something different.
That's a really compelling example. Okay, so wrapping things up, the big takeaway seems to be that FlowRL offers a genuine alternative to standard reward maximization for LLM fine-tuning.
Yeah, it directly tackles mode collapse by shifting the goal to matching the full reward distribution. It leverages these flow balancing ideas from GFlowNets, which implicitly optimizes for both reward and policy entropy, driving diversity.
And the key practical innovations were that length normalization to handle the super long sequences in COD-T, and the important sampling, which is absolutely necessary to make it work with efficient off-policy data reuse.
Couldn't have said it better myself. Those two engineering pieces were critical to translating the theory into practice for large models.
So, looking ahead, what's the final thought here? If these fixes, like length normalization and importance sampling, are needed as sort of patches to make a sequence-level objective like trajectory balance work for 8K tokens. What happens when we go longer?
That's the really provocative question, isn't it? As context windows push towards 16K, 32K, maybe even more tokens, can this sequence-level flow balancing concept truly scale? Or will we need a more fundamental redesign?
Like maybe a version of trajectory balance that operates more locally on chunks of the sequence rather than rely on the properties of the entire massive trajectory.
Exactly. Maybe something that doesn't depend quite so heavily on summing log probabilities over tens of thousands of tokens or needing important sampling corrections over such vast sequence lengths. That feels like the next frontier if we want to apply these powerful diversity-promoting ideas to even larger scale reasoning. Something for listeners to definitely mull over.